Okay, so what we're going to go over in this video is an overview of basics for structural equation modeling. So a lot of this is terms and pictures and just how to interpret some of the words we're going to use all semester. So for this section, you should be reading Burns Chapter 1 and Tabachnik's Structural Equation Modeling chapter, and then we'll go over a lot of these pictures that I'm about to go over. So basic overview of SEM is what we're doing. So SEM stands for Structural Equation Modeling, and it is regression on steroids. So it's mostly a confirmatory procedure, meaning that you have a picture or a model that you're trying to create that exists in the world and you want to test it on your data. And so generally people talk about this as theory-based, where you have some theory, you've drawn out what that picture should look like, you've collected the data for it, and now you're testing if that model in your mind works on the data set that you have. The structural part makes it regression, so it's multiple regressions, and it's a model. So I'm creating these pictures of all these relationships between variables. So confirmatory procedure just means that you don't tend to just fish for things. There are times that we do exploratory confirmatory analysis, which is a little confusing, but the idea is that you had a picture and it didn't quite work, so then you might test some other versions of it to see if maybe you were just wrong on one or two parts. So we're going to model some theorized causal relationships, even though they're not causally measured often. So a lot of these types of data you can't really manipulate, so instead you hypothesize the direction of the relationship, the cause and the effect, but you didn't really test it in a causal way, but you're sort of implying that that's the direction that those things happened. The other cool thing is that it lets you test, move this for a second, there we go, lets you test lots of relationships at once. So I can test 10 or 12 paths with multiple x's and y's, where in regular regression I can only test one y. So this allows me to have multiple DVs. And generally you have to have a theory when you're doing this before, so it's a little less of a descriptive technique and more of a confirmatory technique. One concern, and we'll talk about error terms a lot, is specifying the error terms. And so errors occur in a couple of different places mathematically in the model. And when you're looking at regular regression, it's all one error. So you're predicting someone's score on a test or something, and you have several variables, and any piece that you miss is just error. Now we're going to be able to attribute error to multiple different places. So we don't have to lump the errors all together. Now we can look at errors in one part of the model versus another. And the most important or the most interesting thing to me that takes people some time to get used to when you're first learning SEM is that you're modeling and creating numbers for things that you don't actually have in the data set. So we're testing to determine if our model's any good, that we're capturing this latent variable or this thing in the world correctly, and we don't actually have a number for it to say that we're doing it correctly. So we'll spend a lot of time talking about how do we come up with an overall picture from numbers we do have with numbers we don't have. So let's get into the basic picture idea. So anytime you see an article that's printed a structural equation model, or you're just drawing one for yourself, all of these circles are going to be latent variables. So latent variables are what you're trying to measure normally, and it's abstract. So the easiest thing to think about when you think about latent variables is IQ. We have things that measure IQ, like the Stanford Binet, the WAIS, the WISC, whatever, but I don't actually ever open up their head and see their IQ. So we represent that by a circle, and that's what I'm trying to model. Circles don't have numbers in the data set, so that's the easiest way to remember if something is a column in the data set or not. If it's a circle, no. So errors and latent variables are circles. They are linked to their measured variables, so you have to have some sort of measured phenomenon with your circle, and they're sort of represented indirectly by those measured variables. Okay, so latent variables are the thing you're trying to model. So think about like IQ, or if you've worked factor analysis, these are the factors themselves. But we don't actually have the numbers for them, and we're representing them with these other measured variables. So manifest or observed or measured variables, so they have a couple of names, are going to be squares. And those are things actually measured from your participants. So these can be questions, individual questions or items on a scale. We'll talk a lot about scale development. That could be subtotals of different scores if you wanted to take sort of the average score for your subtotals. They could be counts, so you're not really actually restricted to continuous data. It is sort of assumed, but you don't have to. You can do other things. It could be a lot of different things. It could be gender, so you can use dummy-coded variables. But these are the things that are in your data set that you're using to represent your circles. Now, some other concepts is the idea of endogenous and exogenous variables. So exogenous variables are synonymous with your IVs. So they're the cause. In the model, your exogenous variables are going to be over here. And those are the things that the arrow is going away from. So think about it as X causes Y. And so exo variables are your cause, they're your independent variables. Okay, so the arrow is going out of the variable. And the side note to that, and the reason why I cover this, is because exogenous variables do not have an error term. So changes in those variables are, like any error in that variable is represented by something else. So if I have a reason to believe that this variable has some error, it's because of something I didn't measure. Now, exogenous variables can be squares or circles. I just have the example being circles. So exogenous variables do not have an error term. Endogenous variables do have error terms. So all variables with an arrow coming into them will have an error term. So if I back up for a second, this one would, because the arrow is pointing into it. It has nothing to do with the shape of the object, so if it's a circle or a square, it's all about where the arrow is headed. And the reason that happens is because we have, we're basically saying X causes Y, and so we're using that exogenous variable to predict Y. So anytime we're sort of not getting Y totally correct, it's the error, that error happens on Y. Because we have like the participant score, what I've predicted the participant score to be, based on X, and everything left over is sort of error in Y. So we don't tend to have error, we don't have error on X's. So endogenous terms in general are dependent variables. They're caused by the exogenous variables, and they're going to have an arrow coming into them. Okay. So remember this, because what you don't see when you create pictures using R in diagramming these models is it doesn't show you the error terms, but they're there. They're being estimated in the background, but it doesn't show them to you. And so when you're trying to estimate degrees of freedom and understand maybe why your model isn't running, you have to remember that everything an arrowhead is going into has an error term associated with it. Now, we're going to talk about measurement models. That's most of our CFA lectures, and full structural models. So the measurement model is the relationship between just that exogenous term and its measured variables. So I kind of give a little example right here. Generally, we talk about measurement models when we're talking about CFAs. So confirmatory factor analysis and all of their different counterparts. We're going to do 5 or 6 versions of CFA. But essentially, we have some latent variable that we think causes the answers on these questions. So this one is exogenous. These 3 are endogenous. These 3 will also have errors. And so we think, this is just like EFA, we think that IQ causes their answers on the test we're measuring, or just in general, any personality factors cause their answers on the scale. We don't think the scale creates their personality. We think that their personality is what's shown through the answers on the scale. Okay, so getting used to that directionality. So there's something within them, some phenomenon that creates this output, and we're modeling the phenomenon with that output. So a full structural equation model, or what's sometimes called a fully latent SIM, is a measurement model plus some sort of causal relationship between latents, and it actually can be between squares as well. But it's essentially not the measurement part, it's outside the measurement part. So having a variable that predicts your exogenous latent. And so here's an interesting thing about this particular picture. So this variable here in relation to these is exogenous into endogenous, right? So each one of these will have an error term. But this one is exogenous into endogenous, so this one also has an error term. So a variable can be both exogenous and endogenous at the same time. It depends on what part of the model we're talking about. Right? So for the measurement model, this variable is exogenous. It predicts these squares. For the fully latent part of the model, this variable is endogenous. It's being predicted by this other circle. Okay? And so you have to just kind of break models down into their little component pieces. And so keeping them like the circles that are represented by their squares, and then what's the relationship between the measurement models, and that's the fully latent part. Alright, so something to me makes like no sense is the definition of recursive models and non-recursive models. So recursive models, the arrows flow only in one direction. So that's most of our normal models we're going to do. In non-recursive models, the arrows go back towards the original variables. So for example, this is an example of a recursive model. The arrows flow all in one direction. A non-recursive model is anything that has sort of a backwards, the arrows could flow kind of in a circle. To me that doesn't make sense because recursive definition-wise means over and over again, but a non-recursive model goes back, a recursive model only goes forward. And so really, what am I doing with structural equation modeling? So those are very, very basic terms, and as we get into path analysis, we'll talk more about terms and we'll slowly add more and more of them. But when I'm thinking about what I do with SIM, so generally it's a theory model building analysis. So I am taking theory and I'm building my models and I'm testing if they work. We're going to get that data after we have an idea of what our model should be. We're going to build that model, run that model, right? And then look at fit statistics. So with EFA, we talked about matching the data to a hypothesized model, and you want the difference between those to be very small. So you want your data to match the model. And so generally with hypothesis testing, null hypothesis testing, we want our data to be different from the model, which is a null model. So we don't want any differences. But with SIM, we want our data to match the model. So we're actually predicting the null hypothesis, which if you're used to regular statistical testing procedures, this is what throws people for a loop. Thankfully, there aren't a whole lot of p-values, so we'll give you kind of general guidelines for good fit statistics. But it is different. I want my model to be the null model because that means that's what's really out there in the world. So we're trying to model things that actually exist, and generally we think of the null model as like what's out there in the world. And so we want things to normally be different from the null, which is no differences or no relationships. But in SIM, we actually want our model to match the null, which is what's in the world. So we would examine our fit statistics to see if we were correct. And then in a perfect world, we'd rework and replicate these types of models. And I think in SIM this is especially important because sometimes models don't replicate. They work for that data set, but maybe not another data set. So we really should be exploring when and how our models work. So the way we examine how good we did is model fit, and that's based on residuals. So residuals are technically the error terms for latent variables. And normal regression is a person's score, so the data, the real data that you have for a person, equals some sort of model. So X variables plus error terms are residuals. Residuals in these in a formal picture will be represented by circles. In the pictures that we're going to make with SimPath or SimPlot, it just doesn't show them to you. But remember, we don't have a number in the data set that's error. The only thing we have are these square variables. And so what happens is error gets estimated, so it's a circle. Okay, so remember, circles get estimated, squares are in the data set. Since we're estimating error based on the rest of our model, it ends up being a circle. Either way, we want error to be low. This is always true. So when we talk about basic statistics, we would prefer our standard deviation, our standard error to be small, because that means we have a good idea of what that variable actually is representing. But here we want the error to be low, because low error implies that the data equals the model. And that's what we want. That means we have a fairly accurate representation of what we're trying to model. So we want the error to be low. And so when we're looking at a picture of this, remember that circles, which are either latent variables or errors, they're not in the data set. And then we have squares, which are measured or observed variables, and those are numbers in the data set. Anytime you see a single-headed arrow, so X to predicting Y, that indicates the causal direction, and that could be squares or circles. Any type of double-headed arrow indicates a correlation. So X is correlated with Y, or it actually stands for covariance, but that does not predict a direction. So just like we use regular regression to determine the direction, so these X variables cause Y, and then the double-headed arrows represent correlations. So the relationship between X and Y, we're not sure which way it goes. And here's a quick pause and a side note. We're going to do a lot talking about standardization and scaling. Okay. Standardization and scaling are often thought of as the same thing, but scaling just makes sure that the paths in your model are all in the same scale, whereas standardization just sort of tells you how to interpret it. So a single arrow, right, a single-headed arrow of X causes Y in an unstandardized model is a B. So that's essentially the same thing as interpreting a coefficient in regression. So if X is going up, Y is going up if you have a positive B. So think about those as the coefficients in regression. The harder one is a double-headed arrow is actually covariance. So covariance just tells you how much things change together. We very rarely, in psychology anyway, look at covariance. We often standardize it and create correlation. So if you're looking at an unstandardized model output, you'll see the relationship between variables that are double-headed arrows, and it might be 6,087. And that just tells you how much they're varying together. That is based on the scale of the data. So while unstandardized estimates are really great for single-headed arrows because they're easier to interpret, right? So if I tell you how many videos do you need to watch to get an A in class, I could tell you it's 8 videos. But if I told you it was 2 standard deviations, you're like, what does that mean, right? But if I tell you the covariance between those two things is 8,000 points, you wouldn't really understand, right? So unstandardized estimates to me are really good for single-headed arrows, not so much for double-headed arrows. If we switch to standardized estimates, so this is pretty easy to do where you can actually look at both at once in the output, a single-headed arrow becomes beta. Now don't think of beta as a number that is a correlation. So beta can get over 1. It's a z-score. Okay. So you can think of them as kind of factor loadings in EFA and CFA. But in fully structural models, they can get big. They are standard deviations. And so it's how many standard deviations increase in Y do you get for X. Okay. But double-headed arrows, much easier to interpret now. Those are correlations. So that's standardized from -1 to 1, where larger numbers are stronger, and the sign indicates direction. they go up together, or one goes up, one goes down. Okay, so standardized estimates are useful for CFA because generally everything is already on the same scale. I would say that unstandardized estimates are less popular just because sometimes they're a little harder to interpret. If you ever see SMC, they're talking about squared multiple correlations, or effectively R squared. So you can get an R squared for each endogenous variable. Alright, so path diagrams, and then in one of the next sections we'll get way more into path analysis. But in that burn chapter, she sort of describes that as any particular model. However, when I learned path analysis, they were models with only measured variables. And that is also kind of how the Tabachnik book talks about path analysis. But you've actually already learned some path analysis, you just didn't realize it. So mediation and moderation are types of paths. And so it's a model with all squares where x predicts y, x predicts m, and m predicts y. When we test this in regression, we had to run 3 different regressions to test each piece one at a time. Well, now with sim, we can actually test the whole shebang at once. And we'll do one of these as an example, but you can see that that indirect effect at the same time. So you can test C and C prime all at once instead of doing 3 different regression analyses. Alright, so to give you just kind of to sum up this whole section together, this here is the measurement model where I have this exogenous variable predicting these 3 endogenous variables, so they each get their own little error term. Okay. And so this piece here is measurement. The structural model is this piece out here, and this probably has some extra squares, I just didn't draw it. Where this is an exogenous variable predicting this endogenous variable, so it's got a residual. So you'll notice that the terms are slightly different. Error tends to happen when you have a square. Residuals happen when you have a circle, but for our purposes, we can just call the whole thing error if you like. Technically, they're called different things. So if there is no column for it in the data set, it's called a residual. Sometimes some people call it disturbances as well. Disturbance to me sounds like police work. Residual makes more sense. Things that have a column in the data set have error, okay? Because that is we know exactly how many error points it is, where this is an estimated term. I think it's trying to get the point that this one is estimated from an estimation, where this one is estimated from the actual data. Okay. But you will see that anything with an arrow going into it gets that error term. Okay. What you don't see when you look at these model pictures is that we're actually estimating means and variances. So these models are estimated based on the covariance between items. And so we're actually going to enter on a lot of these in Lavon, which is the package we're going to use in R, the covariance or the correlation table. So variances between all of these items are estimated to help calculate these different terms. And you can also estimate means for each one. And so you have to, when you're calculating degrees of freedom, this is something you have to remember, that even if you draw your picture with all of your error terms, there are other things that are getting estimated in the background that you've probably forgotten about. And so to end this little section with, okay, what do I do with this? So I always am looking at adequacy of the model. So is the picture that I drew accurate, at least as far as I know? So we're going to look at model fit. We're going to talk about chi-square and fit indices. So I have a whole lecture on fit. It is the alphabet soup of fit statistics. I'm also testing a theory. So do the paths match what I would expect? Now in a confirmatory factor analysis, that's kind of easy. Do they load where I thought they would load? But if in a full model or a path model, are the paths that we predict, like, does actually X predict Y? Because we might have a model that's fairly adequate, like it fits okay, but the paths are not significant or in the direction that you'd expect. So what does it look like? Does it match what you were expecting? And then modification indices. So modification indices are a way to sort of explore the data. So you can look to see that maybe this path that you had from this x to this y should actually go to this y. So it allows you to add paths, move them, or delete them based on improved fit by their change. So we'll be able to look and see what mathematically might be a good change. Now, theoretically, it might not be a good idea, but you can kind of use that to gauge maybe you missed something. I can also look at effect sizes. So we can look at square multiple correlations, or R squared. So how much variance am I accounting for in my latent variables? How am I estimating? So I can look at my parameter estimates. So which one is bigger? So which predictor is a better predictor of our variables? And then the end of the semester, we'll get into group models. So we can look at multi-group models. These are some of my favorite things that we can do, or what are sometimes called mimic models, multiple indicators models. So we'll do an example of those both, where you essentially are stacking the data. So you have group 1 and group 2, do they match? But do they match on lots of different pieces in your model? Because remember, models get kind of complex. I have paths, I have errors, I have means, I have variances, so there are lots of things to check to see if they match. What we'll do at the end, now I don't have very good data for these, so you just have to bear with me during latent growth curves, or sometimes called latent curve models. But those are sort of longitudinal pieces. So can we predict the slope change over time? There's multi-level modeling, which is sort of a nested data set type of analysis. Now that tends to be more regular regression. And there's also latent class analysis, where you're trying to put people into groups based on the patterns that are available in the data. Now, some limitations of SIM is that it isn't really causal. Causality is dependent on the research design, not the analysis. So that's why you always hear correlations, not causation. Well, I can run correlations on causal data, and then it would be, but causality, you're sort of implying it by the direction of the arrows that you pick if you make them single-headed, but that just depends on the design, not the analysis. So a lot of these models are not causal because you didn't manipulate the variables, you just observed them. And it's also not really exploratory. You can test exploratory things, and we'll do some of that, but the need, like if you're trying to publish something, the need for that exploration has to be justified, or people will think you're fishing, that you're just trying to build a model to publish. So this is heavily theory-based. And then some just practical issues. You have to have a lot of people, right? This is very similar to EFA. You're building sort of big models. The more people you have, the more believable it is. Because if you only have 50 people, it might be hard to estimate because one outlier is going to cause you problems. So always think about this as more people, more information. More information is always a good thing. That helps me estimate parameters better. It helps me estimate all of the different pieces to just better. Now, large sample sizes don't mean your model will be good. You can have very bad models on very big data sets. But it means that someone doesn't say, well, your model just worked because it was small. The data set was small. So you want large data sets to believe good models. Smaller data sets are sort of harder to believe. And that is the first one. And so we're going to take a break, and we'll come back and do basics 2.